In this video, I want to introduce you to the idea of a differential equation, talk about what it is, some of the terminology we can use to describe them, and ultimately talk about the applications, why we care about these things. So the simplest way of thinking about what a differential equation is that it's similar to an algebraic equation, but instead of just having algebraic operations like multiplication, addition, exponentiation, etc., we now involve some calculus operations. Specifically, we have derivatives. So a differential equation is simply an algebraic equation that also has derivatives. So an equation with derivatives that show up in it. Hence the name differential equations. There's a bunch of terminology that we'll go into in a little bit, but I want to point out that in this class we're going to be looking at ordinary differential equations. That is in contrast to partial differential equations, which is another class that is offered, not at C&M, but that is another class that you could take if you transfer somewhere else. And I'll talk about that difference in just a little bit. But why do we care about differential equations to begin with? So why are these important? Why should we care? And the answer is that they're one of the most practical mathematical tools ever created. Because these equations involve derivatives, i.e. rates of change, differential equations can be used to model any physical process that involves change. So the main reason that we care is they are incredibly useful and specifically they're useful for modeling change. And this could be something from physics, so physical change, social change from sociology, economics, etc. Any phenomena that we're interested in that involves change can ultimately be modeled using differential equations. So this is the idea. And they're useful for modeling change because the derivatives that show up in them are rates of change. So let me give you a quick list of some of the things that we'll be looking at. Not all of these. We won't look at all of these this semester, but many of them. So for example, one of the first things we'll look at is, and you may have already seen this, projectile motion. This is actually, examples of this are done back in Calculus 1 even, and the idea of a differential equation is introduced there. We'll be looking at chemical mixing, so things from chemistry, things like population dynamics, meaning how quickly is a population growing or decreasing based on external sorry, can't write and talk at the same time, based on external factors. So this could be populations of things like, people or animals or trees, or small populations, or populations of small things like bacteria, etc. We'll be looking at things that involve certain types of motion, like pendulums, and springs. Radioactive decay. Cooling and heating of objects. Turns out Newton's law of cooling is related to all of this. And then there's a bunch of other ones. We're going to hit on pretty much all of these. So let me put little check marks next to all of these ones. These are all ones we're going to look at some point or another in this course. But there's a lot of other things that get increasingly complicated. So it turns out you can model electrical circuits. Maybe we'll have time to do that. I'm not sure. Things like cost analysis in economics. So for like a business, for example. Fluid dynamics. So modeling the motion of fluid, and that includes things like also aerodynamics. That fluid happens to be air. So this extends to things like weather prediction, things like combustion can be modeled. Like there's so many things. Financial option pricing. So if you have heard about options in the stock market, people trading options, it turns out you can determine the price of options based on differential equations. So this list includes some things that are ordinary differential equations and some things that are partial differential equations. And again, I will highlight what the difference is in a little bit, but these ones up here with the check mark, these are all ones that we're actually going to take a look at some point this semester. These other ones down here, some of these are partial differential equations, and they would apply to a partial differential equation class as opposed to what we're going to be doing here. So we won't look at all of these, but just some of them. So let me give you, again, just sort of one more sense of what to expect from this semester and sort of the organization. So what we're going to do is we're going to start off with certain types of equations. In fact, I'm going to need to give you some terminology. This isn't going to work unless I give you some terminology. So let me give you some terminology that we can use to describe differential equations. And once we have that terminology, we'll talk about what types of things we're going to deal with throughout the semester. So here's some important terminology that relates to differential equations. The first thing that we're going to be talking about is something called order, the order of a differential equation. So the order of a differential equation is whatever the highest derivative that appears in the equation. So we said that there are derivatives. Differential equations are equations that involve derivatives. The order of a differential equation is just going to be the same as the maximum order of the derivative, essentially. So the largest derivative, largest is a weird word to use here. So let me just say the maximum derivative. I guess neither of these words are great, but the maximum derivative that appears. So in plain English, if we look at some examples, it'll be a lot more clear. This is an example of a differential equation. Something as simple as dy dx equals y. That's a differential equation. It's an equation that involves a derivative. This is a first order differential equation because only a first derivative appears in the equation. Whereas if we saw something that looks like this, y double prime minus 2y prime plus 3 equals some other function, e to the x, for example, this contains a second derivative, y double prime. So this would be second order. So that's all that determines the order of the differential equation. What is the maximum derivative that appears? First derivative, second derivative, third derivative, and so on. Most of the stuff that we're going to be dealing with will be first derivatives and second derivatives. There are certain physical phenomena, things related to bending stresses and elasticity and stuff that would go on in like a civil engineering class when you're looking at like deflection of beams under load that involve up to like fourth derivatives. But typically, most differential equations don't go much higher than that. Fourth derivative is about the highest that you tend to deal with in terms of most physical phenomena that we might be interested in modeling. So that's what order is. The next term that we're going to talk about is linearity. Is the differential equation linear or not? And linearity can be a slightly misleading idea or misleading topic here because we are used to the meaning of linearity in an algebraic equation basically being, an equation that looks like y equals mx plus b, literally a line. We look at the x and we say, well, the only thing that appears is an x to the first power. That's the highest power of x that appears. We also have this constant term, which you could think of as an x to the 0th power term. But this is linear. Whereas if you square it, that's nonlinear. Or alternatively, if instead of squaring it, maybe you add some transcendental function like an exponential or a logarithm, that also makes it nonlinear. The meaning here is a little bit different. So let me take a look at that. The linearity has to do with, the linearity of an ODE is determined by basically looking and seeing whether there are any products or other functions of whatever the dependent variable is that we're interested in, or its derivatives. So let me write this all out, and then again, we'll do some examples to kind of talk about this. So it's determined by whether or not there are any products or other functions of the dependent variable. It's important that we are talking about the dependent variable or its derivatives. So basically, if the answer to this question, I guess I didn't phrase it as a question, but if there are products or other functions of the dependent variable or its derivatives, that makes it nonlinear. If there are no products and there are no other functions of the dependent variable, it just shows up by itself, or its derivative shows up by itself, then it is linear. So if there are, it's nonlinear. If there aren't, it's linear. Okay, so again, I think this is much easier to see via example because that's a big convoluted sentence that we've got there. We could take a look at the ones that we've got up here. Let's look at this one again. I'll do a few more in addition to this, but dy dx equals y. Well, in this case, our dependent variable is y. The way that we've written things, it's clear that y is a function of x. So we're simply asking, are there any products of y or other functions of y or its derivatives? And in this case, the answer is no. Y appears all by itself, y to the first power, and the dy dx appears all by itself to the first power, so to speak. So this would be linear. Similarly, if we do this, let's do this example. So y double prime minus 2y prime plus 3 equals e to the x. So same question. In this case, when I look at it, I see that we have a y double prime sitting by itself. We have a y prime sitting by itself. But there's no products of the y prime and the y double prime. We do have this other function over here, but it's a function of the independent variable x. So it doesn't matter. The fact that we have an e to the x over here, that does not make this thing nonlinear. This is also linear. And it's linear because wherever y shows up, y double prime, y prime, those are the only two things that show up here, they just show up by themselves to the first power. You're allowed to multiply it by a constant, that's fine, but it's not some function of y that's appearing. Let's do a couple more. Let's do this one. Y times y prime minus y double prime equals 0. Well, this one is nonlinear, and it's nonlinear because of the product between y and y prime. The fact that I'm basically taking the unknown thing that we're presumably trying to solve for in all of this, or y, and I'm multiplying it by its derivative. This is a nonlinear relationship between y and its derivatives. Similarly, you could have something like this. You could have a y prime plus y squared. And hopefully it's clear. I will try not to, let me, to make it unambiguous, just so it doesn't look like a power. Let me just write it like this. dy dx equals y squared. This is also nonlinear. Because again, I have a y, the dependent variable, I have a function of that dependent variable here, so it's nonlinear. And this would be the same as if instead of using y squared, if I instead did e to the y, some other function, but again, a function of the dependent variable y, that's enough to make it nonlinear. So this is what we're looking for. You'll have a chance to go through a few of these in the homework and try to identify which type of equation, classify the equations according to their linearity. Those are the two main terms that we're going to be talking about, order and linearity. There will be some other things that come up. We'll have other ways of classifying equations down the line, but I don't want to worry about those now. The last one that I want to mention now is often referred to as the type. And the type just refers to basically whether we're dealing with an ordinary differential equation, an ODE, or a partial differential equation, a PDE. That's what we mean when we refer to type. So the type of the differential equation is determined by basically how many independent variables there are. So it's determined by the number of independent variables. So for those of you that have taken Calculus 3, which is an introduction to multivariable calculus, Calculus 3 is to Calculus 1, essentially, as PDEs is to ODEs. In Calc 1 and Calc 2, we always deal with equations where there's only one independent variable. And in Calculus 3, we introduced the idea of, well, what if there's more than one independent variable? And the same idea kind of extends here. If there's only one, then we have an ODE, an ordinary differential equation. If there's two or more, then we have a PDE. And in general, PDEs are much more difficult to solve than ODEs. And even ODEs, as you'll find in this class, can be quite a headache. So here's how we will classify differential equations. This is the terminology we'll use to classify them. We'll be interested in the order, in the linearity, and for us, the only type that we're going to be looking at, so I guess I should put this down here. So as a side note, we'll only look at ODEs in this class. So you don't need to worry about this last one. But it is good to know that there are other types of differential equations called partial differential equations that involve multiple independent variables. And so these are when you're wanting to model something across maybe space and time, or multiple dimensions of space, etc. Okay, so now that we've got the terminology, now let me give you kind of an outline of what to expect from this course this semester. So what to expect. Basically, we're going to start off with first order linear ODEs. So we'll start with linear first order ODEs. And there is a specific technique that will work on these types of problems, linear first order differential equations, 100% of the time. And then from there, we will relax the constraint of them having to be linear. So we'll stick to first order differential equations. But we'll look at special cases of nonlinear first order differential equations. And when I say special cases of first order nonlinear ODEs, it's because in general, you can't solve all nonlinear, even if they're just first order, you can't solve all nonlinear differential equations using traditional pen and paper analytical techniques that we're going to learn. So we'll be looking at special cases, special types of equations that do have analytic solutions. We'll be learning those approaches, how to solve and how to recognize these types of equations. And from there, basically, we will be done with the first order differential equations. So we'll look at linear first order ODEs, then we'll look at a bunch of special cases of first order nonlinear ODEs. At the end of that, we'll have exam 1. From there, we'll move on to second order and higher order ODEs. And we'll really focus on second order. That's going to be the primary thing we look at. We'll maybe do an example or two of higher order ones, but for the most part, the applications we're going to be interested in will be limited to second order differential equations anyways. So this was what we'll move to next. Most of these are, again, totally unsolvable, even linear ones. So most are unsolvable. And again, when I say unsolvable, I mean using analytic techniques. All of these equations can be modeled or approximated. Solutions can be approximated using numerical techniques. And we'll be talking about numerical techniques as well throughout the semester. So we'll be looking at, primarily here, we'll focus on ones that we can solve, which are going to be mostly what are called constant coefficient problems. So they're going to be linear, and beyond that, they're going to be set up really nicely. So we'll focus on constant coefficient problems. And it turns out, luckily enough, there are lots of applications of these types of problems. From there, we're going to kind of do a mishmash of various things. We're going to look at a method of solving differential equations. So from here, we'll look at a method of solving problems, of solving ODEs, via something called a Laplace, oh boy, if I can write without erasing here, a Laplace transform. And we'll talk about integral transforms in general, but the idea is this is going to allow us to actually solve types of problems that we couldn't solve up here. So you can use Laplace transforms to solve a ton of the types of problems that we will be looking at up here. But it turns out you can also solve ones that have kind of weird and or discontinuous functions involved, strangely enough. So we don't have to have everything be exponentials and sines and cosines. We can have absolute values and things with discontinuities in them. And so we'll talk about that when we get there. But it turns out there's physical reasons that we might be interested in solving problems that involve discontinuities. So these allow us to solve problems with discontinuities. Then at the tail end, we will look at a couple of other techniques. This will all kind of be mashed together. We'll be looking at systems of differential equations. So instead of solving one differential equation, we can solve multiple equations at the same time. We'll look at systems of ODEs, in particular, systems of first-order ODEs. And we'll talk about how you can actually relate these systems of first-order ODEs to second-order differential equations. And we'll look at both linear and nonlinear versions of these systems. So mostly linear, and then I'll talk about some techniques that involve nonlinear systems. And the reason that we might be interested in these nonlinear systems will become clear at the time, but it turns out there's some cool applications of nonlinear systems of differential equations. And we'll hopefully also squeeze in at the very tail end something called series solutions. So lastly, we'll consider series solutions. So put some use to all that work you did at the end of Calc 2 when you talked about Taylor series and infinite series. It turns out we'll be able to solve differential equations and give the solutions as an infinite series, potentially, or maybe even in some cases a finite series. Really, ultimately, the point of looking at series solutions is less for ordinary differential equations and more for partial differential equations. It will be a viable technique if you decide to go on and take PDEs down the line. So these are kind of all the things we're going to look at. Pretty much this will be exam 1. This second order and higher will pretty much be exam 2. And then all this other stuff, there's a ton of it, is kind of going to get mushed together into exam 3. And then we'll have a final exam at the end of all of that. But this is kind of how things are going to be laid out. So the main thing I want you to take away from all of this is the terminology, in particular order and linearity, and you'll get plenty of practice with that on the homework. And just recognizing that the point of this whole class is to finally put some of the tools that you've acquired through years and years of mathematical training, of algebra and trigonometry and calculus, finally put those tools to use, to practical use, and solve real interesting problems that show up in the physical world. These are problems that engineers and chemists and economists solve on a day-to-day type of basis. And so we're going to talk about the techniques to solve them, but we're also going to focus on how we model these phenomena anyway. So instead of just giving you an equation and saying, here, solve it, I want to talk about what goes into constructing a model using a differential equation. In fact, That's what I want to focus on in the next video.